It is very good morning. It is our pleasure to welcome you all to the Knowledge 4.0 webinar series, which is one of the unique and distinct initiative of Chennai for Technology under the guidance of our Honorable Chairman, Sri P. Sriram, who is one of the well-known first-generation successful entrepreneur, Managing Director of MK Group of Companies. Chennai Institute of Technology has been taking tremendous effort in enhancing the knowledge of faculty members, researchers, students, community by conducting webinar series such as technical webinar series, research webinar series, career guidance webinar series, and innovative webinar series, and alumni webinar series. So these webinar series are purely conducted to enhance the knowledge of faculty, researchers, and students community as a social responsibility. So the lockdown period is only for the nation and worldwide, but there is no lockdown for learning. By keeping this as motto, Chennai Institute of Technology has been taking tremendous effort to call the experts from different research organizations, and faculty members from national and international reputed institutes. So Chennai Institute of Technology has been started in the year 2010 by our Honorable Chairman, Sri P. Sriram. Now our institute is being within top 10 among all other private engineering colleges in Tamil Nadu. So today we have 4 eminent speakers from MATLAB, Mr. Nikhil, Dr. Spandhana, Ms. Vinay, and Mr. Agil. So they are with us. It is our great pleasure to introduce all, and I am very happy to welcome all the participants to this wonderful forum. And I hope this will be a very useful forum to enhance their knowledge, and this will in turn help them to go for research using MATLAB for their faculty members and students, and for the researchers too. And also by this forum, the faculty members will get benefit to go for a better teaching in their classrooms. So let me introduce Dr. Spandhana. So Spandhana is an education technical evangelist at MathWorks India. She works with faculty and researchers across India to enable effective use of MATLAB and Simulink in their curriculum and research. She specializes in data analytics, mathematical modeling, machine learning, and deep learning and workflow using MATLAB. Prior to MathWorks, she studied smart actuating systems using mathematical models for her PhD. She graduated with a PhD in chemical and biomolecular engineering from National Institute of Singapore and BTech in chemical engineering from NIT Karnataka Surathkal. It is our pleasure to welcome you, Dr. Spandhana, to this wonderful forum.
Thank you very much, sir. Thank you for the introduction.
Thank you so much. It is my great pleasure to welcome Mr. Vinay Subrahmanya. Mr. Vinay Subrahmanya is responsible for MathWorks engagement with academic and research institute across South India. He works with the industry to embed computational thinking among students and researchers through providing access to various tools and resource networks. Prior to joining MathWorks, Vinay has been a mechanical design engineer at Quest Global and has also been a lecturer in National Institute of Engineering. He holds a bachelor's degree in mechanical engineering from National Institute of Engineering, Mysore, and PG diploma in management from Thambi, Manipal. So it is our pleasure to welcome Mr. Vinay Subrahmanya to this wonderful forum, sir. Welcome, sir.
Thank you very much, sir. Thanks for the nice introduction.
Yes, sir. And it is my great pleasure to introduce Mr. Amith. Amith is an educational technical evangelist at MathWorks and works with the academic institute in India on the adoption of MathWorks workflows in curriculum and research. Amith has been the MathWorks for 7 years and has previously worked with the engineering development group and software development in the image processing and computer vision areas, focusing on workflows for image registration and pixel labeling. His areas of interest includes computer vision, software engineering. Amith has a bachelor's degree in electrical engineering from NIT Surathkal and master's degree in electrical engineering from University of Minnesota. It is our pleasure to welcome Mr. Amith to this wonderful forum. Welcome you, sir.
Thank you very much again, sir.
And it is my great pleasure to introduce Mr. Nikhil. And Nikhil, if you are able, you can switch on your video. And Mr. Nikhil is an application support engineer at MathWorks. He works with the engineering development group and has started with the technical marketing at HAL Goda teams. Nikhil holds a bachelor's degree in electronics and telecommunication from Visavarma Institute of Technology, Pune, and master's degree in biomedical engineering from IIT Bombay. It is our great pleasure to welcome you, Nikhil, to this wonderful forum. It is. Thank you so much for joining with us. It is our wonderful moment to learn from you. Please, you can go to the session, sir.
Thanks, everyone. I'll be beginning today's session. So let me briefly share my screen. Okay, good morning, everyone. So today's first half is about AI in engineering practice, education, and research. So we'll be looking at what is the AI workflow and how MATLAB can enable this workflow. So let me begin by sharing an interesting statistic. So this graph that you see here has been published by Gartner, that is a research and advisory firm that analyzes a number of companies and also a number of technologies that are currently in hype. So in this report, Gartner says that in 3 years, there is a prediction of almost 10-fold increase in the number of AI projects. So what does this mean? This means that integrating AI is almost a priority for every company that exists here today. And what are the what are the barriers that are present in successful adoption of AI workflows? So Gartner says that the first important barrier is the skills of staff. So what that means is currently available staff who are experts in their respective domains are probably not able to or are not ramped up to work on AI related problems. And the second important problem is about the data quality. So nowadays there's humongous amount of data that is available, and data comes from multiple sources and stored in many databases, and they're scoured and they're analyzed, and then they're prepared for building an AI model, right? But the quality and the amount of preparation work that is needed to make it of good quality is tremendous, and the staff should be adequately skilled to work with this kind of data. So these are the two important barriers that Gartner recognizes for successful adoption of AI. And some other reports also confirm this. Like, for example, this is a McKinsey report, which says that skill sets of AI is as the second place. And also a number of teams in current industries, they work in silos. Like, for example, design engineers work on design problems in a design team, and mechanical engineers work on specific mechanical engineering related problems, and these are just silos within the same organizations. And these kind of silos, they prohibit building an end-to-end AI solution. So when we are thinking about a system level solution for a specific problem, we need an end-to-end solution and a platform that can enable this end-to-end solution. So MathWorks is the parent company for products known as MATLAB and Simulink and many other associated toolboxes. So the same Gartner research and advisory firm has recognized MathWorks as a leader in the completeness of vision and has placed MathWorks in this quadrant, as you see. On the axis are completeness of vision versus ability to execute, and they've measured number of companies in this space like Google and number of Microsoft, number of other companies which are in this space, and it has placed MathWorks in the leader quadrant. So what that means is the tools that are available with MathWorks, they empower any engineering team to accelerate the production of an AI model or designing a system level simulation, and they fit perfectly in the workflow for every company. So when we are talking about building an AI algorithm, we are looking at these 4 steps. So every company that is working or to build an AI model will first acquire data, and then build a model that can represent that data, and then build a system. If they're thinking about hardware deployment, they have to build a system and model the system, and then plug this model in and verify how the data that has been acquired and the model can integrate with this system to provide the necessary functions, and then finally deploy it. If you're not understanding what I'm saying, I'll give you an example and explain each of these steps in the coming slides. So let's see what is the first step. The first step is data preparation, right? Nowadays, we have data from multiple sources. We have data from sensors. We have a number of, say, data like from Facebook or Google Maps, for example, is one such repository where there's humongous amount of data. And all this data should be acquired and cleaned. And that is one of the most challenging steps sometimes in the entire AI workflow. Once this data is acquired, one needs to model this. That means we have to make sense of what that data is depending upon the type of problem that you're attempting, right? When we are thinking about building a model, we have to look at choosing the right algorithm, tuning parameters, and then training the model itself, which can also be quite complex because we'll need to make use of different types of hardware to accelerate this process of training. And also sometimes if your reseller partners or if your team members are working with different platforms, the software that you're using should be interoperable. That means the same model can be built in multiple platforms and they should be able to talk to each other, right? Now, once you complete the model, we are going to think about how it integrates in a complex environment. Say you're designing a self-driving car, you've acquired this vehicle or traffic data set, and you have labeled it and built a deep learning model, and then now you want to deploy it so that your self-driving car, based on the based on what it has learned so far, that means it probably learned how to navigate through a complex environment, and now the self-driving car has to make decisions, and that comes when we are able to deploy this deep learning model on a hardware, and this hardware which has to control the systems in the car. So it has to control the steering or the brakes and so on, right? It has to be able to control various systems in the car. So we have to see how this model can integrate in a complex environment, and also it should be amenable to deployment. That means it should go on to various devices. Sometimes deployment could be on hardware, it could be as an app, and or it could be on edge devices. That means say controlling a controller or something like that. So these are the 4 steps. So I'll give you a little more detail into each of these steps and what are the challenges that exist in these steps. So the first step of the AI workflow, that is the data preparation. So what we are doing here, we are going to collect a lot of raw data, and then we are going to clean it, and we have to make it useful basically. So so this is one slide which I find really interesting. That is a difference between academia and industry. So this is Mr. Andrej Karpathy. He studied at Stanford. What he did, he currently works at Tesla, and in his talk a couple of years ago, he mentioned this a huge disparity between what he did when he was doing his PhD versus what he does in his role in Tesla. So in his PhD, he worked with a limited amount of data sets, but spent a lot of time focusing on models and algorithms. That means building newer models, building better algorithms, and so on. But when he joined Tesla, it was slightly different. Like what he had to spend almost 75% of his time on the data set itself. That means acquiring the data, collecting it, and building teams to do this itself was a huge task for him. So this is a huge disparity between how academicians work and between how industry works. So while academics are very focused on building newer and better algorithms and models, and focusing not so much on the data set, they work with whatever is available. The industry has to work with a lot more complex data sets. So what do you mean by working with complex data, and what are the challenges that are existing in this data preparation step of the AI workflow? So one such preparation is step that is data cleaning and labeling itself. Sometimes the data that you collect, if it is a time series data, it could come in various timestamps which are not synchronized, right? So in such cases, you will have to build algorithms that can synchronize these time series data. Or if you're working with audio data set, you can have a very noisy signal, a lot of background noise and so on, which you have to build models to remove all that noise. And if you're working with a video data set, for example, what is shown here, you'll have to work with, say, labeling of this video data set. Where does something like this be useful? Say, you're deploying a model in a self-driving car. What you are going to take one data set of the complexity of the navigation algorithms, that what needs to be navigated. So we collect all this data set, and then we train an algorithm or train a model to understand what is the road here, which ones are cars, and where is the stop sign, and so on. So we need to build this data set and label it so that this labeled data can then be fed into our AI model, and then this labeled data is used to train our AI model instead. So this labeling process itself can be a huge task, right? Imagine working with a number of frames of this video and manually labeling each of this. It is a really huge task. So in MATLAB, you can use our workflows like we have a labeler app known as image labeler app, where it's a very nice environment for you to label uh, this kind of data. I'll share all these resources with you later on. So if you're interested, you can look up later. If you have some questions, please put them in the chat window, and one of our staff members will answer it. And if you're interested in any of these workflows and request more information, put it in the chat window, and we'll be happy to share the links so you can browse them. The second part of the workflow is the building the model itself, right? So for building the model, you will need multiple algorithms. If you're working with machine learning, you will be working with decision trees or SVMs and so on. And if you're working with deep learnings, you'll be building CNNs or different types of networks like LSTMs and so on, right? So for working with all these type of algorithms within MATLAB, we have statistics and machine learning toolbox for machine learning, and deep learning toolbox for deep learning, reinforcement learning toolbox, and all these number of toolboxes support this AI workflow. And we have a number of other toolboxes like image processing toolbox. We also have computer vision toolbox. So it's not just limited to the algorithm itself, but a number of associated products which can help you in building your end-to-end system. And all these, we also have pre-built models, like say, for example, in deep learning, if you're already working in deep learning, you should be familiar with these pre-trained models known as AlexNet or GoogleNet and so on. And all these are already available with just a single line of code. So all these apps can be used for accelerating your workflow, and they also give a very nice user interface, which are drag and drop based user interface, where you don't have to spend much time coding, and you can visualize how the network looks like, or you can visualize what the output of a machine learning model is. So what you see here is a deep network designer app where you can drag and drop different layers in your network, and then train it without writing a single line of code. Similarly, we have classification learner app where you can load your entire data set, visualize it, choose different types of models, and then see which one would best suit your application. So all this without having to write a single line of code, you can visualize, you can also finally generate scripts for the entire network that you built or the model that you've chosen here. It's fairly straightforward for a person who doesn't know MATLAB or doesn't know machine learning and wants to explore. These are the places where you can get started. Typically, when you're working with, say, if you're building a deep learning model and you are having a data set and you've finished the first step of the data preparation, and you want to build your deep learning model, typically it is a very time consuming process. If you're working with limited hardware, you'll have to scale up your training process using cloud platforms or using much more sophisticated hardware like GPUs and so on. So when you want to do this, your deep learning model or deep learning platform that you're using should be easy for you to scale up for training, right? So here we have collaboration with AWS and Microsoft, where you can directly train your network on cloud. We have MATLAB Dockers within the cloud containers, and you can use MATLAB on the cloud using your existing license, and you can, without having to write too many lines of code or migrate your program from your local desktop to the cloud, you can very easily and seamlessly make use of cloud platforms, as well as much better hardware like NVIDIA DGX systems and so on for your training process. Similarly, if your colleagues are working with different platforms, like typically in deep learning, we know that in this deep learning world, multiple companies like Google, Facebook, they all are supporting various platforms like TensorFlow and PyTorch respectively. So these people typically choose to work in one of the platforms, and say if you want to import from one platform to another, say you like the MATLAB image processing workflow, but you want to build your model in PyTorch, you can seamlessly integrate it. So through the ONNX platform, that is Open Neural Network Exchange, you can bring MATLAB models, you can take MATLAB models to PyTorch, or you can bring MATLAB models from PyTorch into MATLAB. So we have seamless integration with various other platforms, and this is what we mean by interoperability of with other frameworks. So let me give you an example and explain what we mean by the third workflow or system design workflow. Say you're building an automated driving system, and here the red car that you see, assume that it is an automated driving, self-driving car. So what kind of algorithms go into this kind of self-driving car? It should be able to perceive its environment. That means there are perception models that should be there, and it'll have number of sensors to know what is happening in the surrounding, like LiDAR sensors. It'll have a number of sensors, and all these sensors send data, right? This data has to be collected, and it has to be analyzed. It has to be fused and analyzed. So we have a number of tools that can support this kind of problem complexity involved in building such a solution for such a important problem. So this self-driving car will use AI for perception, and it should integrate with the models that are used for say controlling the car, steering the car, and so on. So from within MATLAB and Simulink environment, Simulink is you'll see what Simulink is in the second part of the presentation today. So in Simulink, typically our automobile customers like Honda, Hyundai, and so on, all of these automobile customers have Simulink models, which they use for their control systems and so on, right? So within the same, using the same platform like MATLAB and Simulink, you can have your control algorithms in Simulink, you can have your AI models in MATLAB, and then you can integrate all of this to build a system level simulation of this entire for this car basically. So this is fairly it is straightforward, and it is something that can be done in one platform. Let me give you an example. This is a startup company known as Voyage. So this company makes self-driving cars for retirement communities, and they were able to deploy a level 3 autonomous vehicle within 3 months. This is almost a very impressive task for building such a complex model within 3 months. And what they did, they used our ROS toolbox, they used our Simulink platform, and they integrated it with a deep learning toolbox and so on for building their models. So these AI models that are built, they need to be deployed. So deployment could be as simple as deploying it on some embedded device, like say a card that will go into your self-driving car, or it could be an enterprise level system, like it could be an app for financial industries, or it could be something on the edge edge devices. That means, say, in your factory, where the data that is collected by the sensors in your factory is analyzed on the cloud, and then a controller has to take action based on the data that is analyzed in the factory environment. So models can be deployed anywhere pretty seamlessly using MATLAB. So how is that done? MATLAB has a very impressive code generation capability. You can target multiple hardware like CPUs, GPUs, or FPGAs using our code generation capabilities. So within the MATLAB environment, typically engineers build their application logic, and once that application logic is verified and validated, when you decide which hardware you want to target, like say if you are targeting a GPU card, then you'll have to translate this MATLAB code into CUDA code. And we have a platform, we have another product known as GPU Coder, which can do this automatically. What this does is it reduces the number of errors in your code, because it is automatically converting the MATLAB code into a respective hardware dependent code using target specific libraries. So you don't have to spend a lot of time rewriting the code for different hardware that you want to test. And this is very important in the industrial setting, because typically it's a trial and error approach based on which hardware would be very useful for deployment. So say, for example, you've targeted one NVIDIA card first. That means you're writing it in a different language. So next time, if you want to target on an Intel GPU, then probably you'll have to make use of different libraries and so on. So you don't need to rewrite your code at every stage. So MATLAB makes it pretty easy for deployment, and most of this is one-click deployment. I'll give you an example of what one university called Ritsumeikan University in Japan, why did they use deep learning and how they use MATLAB for deep learning. So basically, one professor in Japan wanted to reduce the radiation exposure in CT imaging. So typically, CT scans, they need a very high dose of radiation, right? So what he did was he wanted to use ultra low dose CT and then enhance the resolution using deep learning techniques. This low dose CT might not give a very good resolution, so he used deep learning techniques to enhance the resolution. This is known as super resolution, and he used MATLAB to train his CNNs for various images, and then used GPU acceleration for training his models on multiple GPUs. So in this way, he was able to build an AI model, and he plans to deploy it in a clinical setting. So this is how one university made use of MATLAB for their research purposes. So why are we talking about MATLAB and Simulink for AI? It is a unified platform, and it reduces the time and effort that is required for labeling and pre-processing with various tools that we have, like labeler apps and multiple other apps that we have. And this entire workflow, MATLAB supports end-to-end workflow all the way from data preparation to the deployment stage. And it's pretty standard nowadays in industry, where people are already using Simulink for building models, and now we have capabilities for AI workflows in MATLAB, and integrating this two has become much more simpler in today's world. So this is one report that we see, I think this by BCG, and what this talks about is what is the AI effect on the workforce today. So what they see is that existing workforce, like in the poll that they conducted at an organizational level, 84% of the existing workforce will need to change their skills to adopt AI in their workflow. That means they already are domain experts, and they have to acquire these skills for understanding and building AI models. So what does it mean for institutes today? So we see that there's humongous increase in the number of job postings which require machine learning and AI skills. Where do these job postings come from? Like companies like Microsoft, Google, and so on. And they are looking at hiring a lot of people who have these kind of skills. And one good thing about having one good thing about having these kind of the fact that Microsoft or Google are looking for engineers who have talent in the AI workflows is the fact that it is irrespective of discipline. So your institute might have multiple disciplines like mechanical engineering or electronics or biotechnology. If there is a student who is interested in data analysis or statistics or mathematics and building algorithms or making sense of data and so on, encourage them to look at machine learning and deep learning workflows, because these are getting adopted in almost every industry these days, and there are a lot of opportunities that are available. So where can you get started? We have two free courses known as machine learning on ramp and deep learning on ramp. One of you, Nikhil or Amit, could you please post the links in the chat window? We have these free courses which can give access to MATLAB through your web browser. They have very engaging video lectures and hands-on tutorials. So you can suggest your students to take these courses. They are free, they are 2 hours long, and at the end they can get a certificate of completion. So you can see what is in MATLAB for machine learning and deep learning and get an intro to this using these courses. Overall, I want to conclude saying MathWorks is enabling the AI workforce of tomorrow. We have 6,500 universities which are teaching MATLAB, and we have almost 1.3 million students who are using it, and tens of thousands of skilled graduates are entering the workforce each year. Thank you very much. So Amit will take over from here. If you have any questions, I'll be happy to take at the end of the presentation.
All right, cool. Thank you, Spandhana. Let me quickly share my screen here. Okay. So if you can give me a minute, I'm going to open my presentation here. So I'll do slideshow from the current slide. Okay. Can you see my screen?
No, sir, we are unable to see.
Yep.
Good, you can go ahead.
Set it up.
Yeah, fine.
Right. Okay, cool. Great. Thank you, Spandhana, for the introduction on AI. So my name is Amit. I'll be talking now about model-based design and system engineering, which is sort of the other spectrum of what we do at the MathWorks, right? So really, to motivate this, I'm going to be very quick. There's a lot for me to talk about, but you know, half an hour may not be sufficient to go through all of this. So so please bear with me if this is faster than normal. Also, hopefully you can see me now. But I'm going to go through very quick, and we'll answer questions later on. Okay. So to motivate very quickly why model-based design is important. Imagine these are the, these were vehicles maybe 30, 40 years ago, with no fancy features. But if you look into the future, and even now, in fact, there are several of these engineering kind of features which are standard in vehicles, right? Like power windows now is pretty much standard. Just yesterday, I heard about a new vehicle which has voice-controlled sunroofs, right? So you can open the roof of your vehicle just by saying "open sunroof," and then the roof will open. Right? So the point I'm trying to make here is engineering systems these days are getting far more complex and far more integrated and interdisciplinary in some sense, that you can't just work in your silos, pretty much like what Spandhana was mentioning. Everything has to be sort of well integrated, right? So that's sort of the direction in which we see most engineering sciences moving towards, right? So sort of quickly an agenda for the next 30 minutes or so. We'll cover 5 topics. We'll spend about 10 minutes on the first one and then 5 minutes on the others. And at any point in time, if you have questions, please do, like you've been already doing, ask in the chat window. And if you don't want to ask questions here, but want to email us, I'll keep flashing this up every now and then. So please note down our email addresses and reach out to us after if you have questions there. Okay. So we'll go to the first topic with the background that systems these days are getting more integrated and interdisciplinary and complex, right? So why consider model-based design? So the traditional engineering development process is kind of like this, right? So you start with some requirements, you then come up with specifications, which is, codify these requirements into some kind of a list of things that you need to build or develop and design. You then go into design, where depending on what the areas or domains are, you potentially do them separately. You then go into implementation. Once you've got the designs, you say, okay, these designs are good enough. I'll implement it in code, potentially embedded software. And then finally, you integrate and test it all together, right? The challenge here, unfortunately, is that each of these portions of your design are done sort of independently, right? There's no crosstalk or there is no integration as much as there needs to be between these. Let's say the electrical design happens separately from the mechanical design, and then there's not much crosstalk, right? So the problems here really are the requirements are difficult to analyze, and let's say the requirements change, what happens then, right? These are easy to interpret, difficult to integrate. The physical prototypes are, when you design and implement it, if you build it immediately, it's more expensive and more difficult to make changes as time goes by, right? And then manual coding. So, all of this HDL code, C++, or even structured text, right? You'll have to write them manually on your own, which could introduce defects as well, right? And then traditional testing. So you test once you do all of this. And then, if you find something that's broken in testing, you'll have to go all the way back and fix it, right? So which is also challenging. This is hopefully the video will play. You may have heard of this space program, this thing called Ariane 5. In 1996, what happened was on takeoff, within a few seconds, it just crashed, right? This is terrible, right? Very unfortunate. Fortunately, there were no people in it, but what I want to indicate here is that the traditional design process can lead to failure like this, right? So model-based design, what is model-based design? So this design process here, these sets of things that you need to do, is replaced by sort of an integrated platform and a modeling environment, right? The research and requirements feed into this as earlier, but now it's all in one kind of environment, one kind of platform, right? Where you do both mechanical, electrical, and the software part of things, everything in one platform, right? The implementation also is quite well integrated here, meaning that with the same kind of design artifacts that you have, if hypothetically you could generate code to target C++ on microcontrollers, HDL code for FPGAs, or even structured text for PLCs, that would be great, right? And then finally, with integration and testing, the difference here also is that this is sort of a continuous and iterative kind of process, right? So once you have this one framework and one kind of a system to do all of this in, it becomes that much easier to keep looping through. And essentially, if you detect errors in the testing phase, you can go back more easily, make corrections, rerun the entire loop, and make sure everything's working, right? The environment is a single simulation environment or implementation environment too. So the design can be optimized. So you make a change in the design, the process of going through this entire design or development process is that much simpler because you have one environment and it's easy to go through everything, right? Lower costs, so you can use hardware in the loop testing if you'd like, where you can build easy or simple implementations first, test it and make sure it does the right thing, and then keep increasing complexity over time, right? So that way you don't spend too much time building physical components that you can't change later on, right? And essentially, if you can automatically generate embedded code, so from your design itself, if you could generate code that target these languages and these hardware, that'd be great too, right? So that's really what we'll be talking about in the next 20 minutes or so, very quickly. Here's a case study, and we'll share hopefully this presentation with you later on. And you can go on to this link, which talks about this particular, it's a Indian company called Ether Energy, and they used model-based design to build these scooters, right? So these are electric scooters. They have charging stations. It's fantastic, right? They reduced testing time, for example, by 50%, right? So that's significant, weeks and not months, right? So please, if you're interested in learning how the industry has used model-based design, please consider looking at this link here, okay? So at a very broad level, what are these industry standard MathWorks tools, right? So there's MATLAB, which is our programming language, and Simulink, which is the tool that I'm going to speak about a little in more detail, where we do this thing called model-based design, right? So let's focus on Simulink for the next few minutes, right? We understand most of you folks are in academia. You're either teaching faculty or students. And so the question comes up as to how do you get started with this kind of process of thinking early on, right? So we've shown industries, but even in India and across the world, use this process to speed up their engineering process, right? Speed up or make more efficient their design process. So how do you get started with this in your university, right? So one of the things that we are very excited about is this thing called project-based learning, right? So it's a comprehensive approach to learn things such that students are engaged in investigation of real-world authentic problems, right? So, for example, here's hopefully the video is playing all right. Here's a Lego NXT robotics kit where it's trying to solve a Rubik's Cube sort of autonomously, right? And here is the Simulink model, and I'll come to what Simulink models are. That is doing this, right? So your design, your implementation, everything sort of is sort of represented by this. You can automatically generate code that runs on this particular Lego board from the Simulink model itself, right? So this is one example of how students can get started with this kind of a design philosophy as early as possible. And if you notice, there's very little textual code, right? You don't need to sort of learn C++ or HDL to do this. This is all block diagram, right? So another specific example of how a university has used this is Kaili Tech in Hubli in Karnataka. So in the first year engineering program that they have, all departments, 1,200 students from first year, they have a course called Engineering Exploration, where the focus is to do problem solving rather than coding, right? So this is called experiential learning. There's a lot of stuff that they build. For example, over here, here's a line following robot that they've built. Here's another example of, if you notice, they have this accelerometer, I believe, over here that can measure what's happening and things. So really, this is called the Joy of Engineering course. And so this is how universities have kind of started using and developing their model-based design workflows. All right. So here's another sort of quick video about how a DC motor can be simulated. Here's a state diagram model, and here's an entire engine really simulated in Simulink, right? So I'll move quick now because of time. But in Simulink, which is this framework, there are all of these kinds of systems that can be built, right? So it's a multi-domain modeling platform where essentially you have these sort of block diagram kind of approaches where it can be both continuous time as well as discrete time, right? We have various solvers. So, these are very complex systems. We have solvers that can handle very difficult dynamics and manage to give you accurate enough results. And we can reuse MATLAB and C++ code. So if you already have C++ code that can do something for you, you can reuse it in Simulink, in these blocks, for example, right? So as a case study, for example, if you want to model and control a DC motor, the hardware will look like this, but from a mathematical and simulation perspective, how does it look like, right? So essentially, this is a bunch of differential equations. This is the equivalent circuit, right? There are various components here. These are the electrical components. There are various parameters or values that you want to measure and write equations for, right? So this is the over here the torque equation, right? And there are different components of it. And here's the electrical equation, and there are different components there. And so essentially, this boils down to a set of two differential equations, right? Which we want to solve. Now, if you can build a system that can simulate this, you can essentially model the DC motor, right? So in MATLAB, in the interest of time, I'm not going to open this and show you. But in Simulink, in this platform, it kind of looks like this. So you can add pictures of what you're trying to do. You can include your equations. And these are the blocks that can simulate this, right? And you can also have graphs. So as soon as you hit the run button, you can find out what each of these signals are doing. So in this case, for example, your angle of the motor is going from 0 degrees to 90 degrees, and the current and voltage, I believe, is sort of changing this way over time, right? You can also build controllers fairly easily. So we have blocks for PID controllers. If you want to design this as a state machine, we have tools to do that. And integrating existing code, you can do that fairly easily as well, right? I know I'm going very fast, but I'm hoping to give you a broad understanding of all of this, and you can take a look at this in more detail later on. Okay. All right. So in terms of the next topic, we were just briefly talking about state machines and so on. Let's quickly jump into state machines and discrete events, right? So the DC motor model that we looked at is something called a time-driven system, right? So it's a continuous kind of state. Your dynamics are differential equations, right? But you could also have event-driven systems where it's a discrete state and your dynamics are difference equations now, right? You can also model event-based systems using this thing called flowcharts or state machines, right? So these are, fairly complex, logic that we're trying to simulate, where we have sort of states and then transitions, and then you can sort of program based on these states and transitions, right? You can also do event kind of simulations where if you're doing things like a queuing system, we have some blocks that can help you simulate those kind of systems as well, right? You can do scheduling, for example, and say this event happens first and then wait for the other event to happen and then do the third event and things like that, right? So we have models that can do that, right? So Stateflow is this other kind of platform where you can sort of drag and drop and create these states, and then you can define these transitions between them and say, okay, I start in this state, and then if this event happens, I then move to this state, and then if this event happens, I move to this, and so on, right? I'll point you to ways to learn this in more detail later on, but hopefully you get the big picture idea of what kind of systems can be simulated here, right? So things like fault management or task scheduling, all of these are examples of systems that can be developed or designed using this Stateflow platform, right? So again, this is a fault management system where you start here, and if something happens, you can either go to standby or you can move into this state where there's a check. It can either go here and then come back, and so you sort of get the drift, right? So these are state machines, and these can be modeled well in the Stateflow modeling environment. Okay, so quickly again, jumping domains now to physical modeling. So if you're from a controls or a mechanical engineering background, this may be very familiar to you, where you have inputs, you have a controller, you have a plant model, and then you have this feedback loop, and then you sort of find out what kind of controller you want to use to operate this particular thing, right? Now, it's important to get a good enough representation of your plant itself. And to do that, there is this other platform called Simscape. Okay, so you can sort of build representations of several of these systems through Simscape, and that will give you a good enough model of what you're trying to do, right? So specifically, for example, if you want to simulate this kind of a circuit, right, you can, Simulink is known for signal-based modeling, but with Simscape, you can kind of design equivalent circuits like this by dragging and dropping these discrete blocks here, right? So you have resistor blocks, you have a capacitor block, you have an earth block, and you can sort of build these physical networks and solve for current and voltage, for example, by constructing these networks as physical networks, right? You don't have to go into the mathematics of it. So in Simulink, you kind of build mathematical kind of models, but in Simscape, you can build models directly from these components, right? So for example, for those of you who are from a mechanical background, if you're building a sort of a mass spring damper kind of system here, this is the equivalent circuit in Simulink, right? And I can play this, and you see how to build it. So these are the gain blocks, these are the integrator blocks, right? But in Simscape, it kind of looks like this. So you have mass blocks, you have resistor blocks, you have the damper block, and so on, right? Now, the real advantage is if you want to add one more element here and make it a two mass system, see how this looks like in Simulink and see how easy it is in Simscape, right? So that's really the power of being able to represent your elements as discrete physical blocks here, right? With their physical characteristics included. So having seen that, I'd like to now show you all the different domains that we have blocks in. So if you notice here, these are all the domains that we have something called foundation blocks in. And so, just like the resistor that I showed you, there are several blocks in each of these domains that you can use, right? Beyond that, we have more specialized blocks in all of these more specific domains, right? For example, if you're in the electrical machines modeling space, we have models or blocks for electric drives, power converters, and so on. And each of these are backed with sort of well-tested components, right? If you're in the robotics area, for example, we have a lot of blocks that you can use for doing 3D dynamics and kinematics and so on, right? If you're doing fluid mechanics, there's a whole bunch of blocks here, right? Really, if all of this was too complicated, here's the real deal, right? So going from your system specification to your model itself, if you do this, let's say in traditional languages, you need a whole lot of domain expertise, and you need to put a bunch of coding effort here, right? With MATLAB and Simulink, we kind of reduce the coding effort a little bit, right? Because now we have mathematics blocks that you can use directly, but you may still need the domain expertise, right, to model these things in math. But with Simscape, what happens is domain as well as coding effort is reduced because we've kind of codified that into these blocks itself, right? So that way, it's much faster for you to go from specification to model using Simscape, right? And if you're interested in a DC motor model, for example, here's a video which you can look at later on. Okay. All right. So quickly, I know we have 2 minutes in our scheduled time remaining, so I'll try to jump through some of these slides quickly, and we can have more questions later on. Okay. So we know most of you are either faculty, teaching faculty, or students, and so we'd like to quickly talk about how this can be used in curriculum, right? So this is AICTE, the website, has a model syllabus for the electrical engineering undergraduate program, for example. And if you notice, several of these courses can make use of either MATLAB or Simulink to make the concepts to be learned much easier. Okay. Beyond that, you can do this online. So if you have a license for MATLAB and Simulink, there's this new thing called Simulink Online, where you can do all of this modeling in your browser itself without having to download or install anything, right? Also, here's a link for MathWorks Academia. Essentially, other professors from all over the world have shared their course material. And so you can use this royalty-free in your own course if you like as well. And that way you can sort of get a jump start. You don't have to start from scratch. You have a base to start off with already, right? Just like Spandhana mentioned about the deep learning and machine learning on-ramp courses, there are equivalent Simulink and Stateflow on-ramp courses as well. These need installed Simulink at the moment. So you have to download and install MATLAB to do this, MATLAB and Simulink to do this. But they are otherwise 2-hour courses, which is a high-level introduction to both of these topics. Okay. All right. So that was a quick 2-minute walkthrough in terms of use in curriculum. So I'll quickly summarize now that it's already 10 a.m. in the morning. The takeaway I want you to remember is there are sort of 2 different modes of work, really. So there's the simulation world, and then there's the physical interaction world, right? In the simulation world, Simulink is this platform where you can sort of build very complex systems. In this case, for example, a transmission controller, right? All within this block diagram framework. And the applications are several, right? So controls, signal processing, communications, you name it, you can sort of model it in Simulink, typically, right? There are caveats, which we can go into later if you're interested. Here's a Lego MINDSTORMS kind of a demonstration very quickly. So this is a robot that you can build a system here in MATLAB, or model here in MATLAB to make it self-balanced, right? So it has only 2 wheels, and so sort of to build the controls and the state machines to make it self-balanced, right? You can use Stateflow and Simulink to sort of simulate this before you actually build it, right? The build it part is really this physical interaction part, for which also we have some solutions where you can generate code, right? So earlier in a previous slide, I mentioned, what if it's possible to go from your design automatically to any of these coding frameworks and go into your hardware easily, right? And you can do that. So Simulink model, Stateflow, and MATLAB, you can generate code. And we can share links later on if you're interested in this kind of workflow to do this quite easily, right? So, pictorially, really, you have your Simulink model, you have your algorithm and your physical model. You can generate C code if you wish, and deploy it automatically very easily on your hardware prototype if you have, or if you want to use other simulation environments or other hardware, you can do that too, fairly easily, right? There are steps to do it, but it's much easier than otherwise, right? So just to round up and summarize, model-based design is a paradigm shift in the way you think about engineering design. The idea is to not worry about the nitty-gritty details about code, but is to focus more on the math and algorithm, right? You don't have to hand code this anymore. We can automatically generate C++ or HDL code. And this whole pipeline or this whole workflow is well integrated now, that you can do testing and sort of move into this kind of rapid prototyping kind of a model more easily than otherwise, right? And the result is that your innovation speed or your experimentation speed can be much faster, okay? So that you're in academia, I think it's very important to start early and focus on the engineering and science part of it rather than programming, like we mentioned earlier. Sort of learning model-based design really helps you to build that kind of mindset early on, that building complex systems doesn't have to be complex and can be done in a well sort of organized and set up framework like Simulink is. Okay, so that's it really. So sorry I went 4 minutes over, but thank you for your time and attention. Several math workers, people who work at the MathWorks are called math workers. So several of them have helped us build these slides and these demonstrations. If you have questions for sales inquiries, please contact Vinay, who's here on the call. This is his email address. And if you have technical questions, please do contact either me, my name is Amit, or Spandhana here at this email address. Okay. Thank you very much for your time, and I'm guessing we can take a few questions.
Yeah, thank you so much. Thank you so much, Mr. Amit and Dr. Spandhana. And so it was a wonderful presentation. We believe that certainly this will be very useful for researchers, students, and faculty to enhance their knowledge. And thank you so much. Now I request Mr. Vinay to consider the question and ask the questions.
Definitely. Thank you, Professor. So let me just consolidate the questions and then ask a few of them. Let's take a few of them right away. Professor Tirumurthy has asked, does MATLAB have community support or any preconditions? So this is a question from Mr. Tirumurthy. Do you like to answer that?
Right. So this is Amit again. I don't entirely know what community support means, but Nikhil just sent a response to you. So there are groups of people who already use our tools, who answer questions if you have any, who share their models and code if you're interested in. So there is a community in that sense. You can post questions if you have, and there are people who answer it, both within the company at the MathWorks and our users as well. So there is support in that perspective. But if you're looking for something more specific, please do let us know and contact us, and we can try to answer this more.
Right.
I have one point to add to Amit's points. So in MATLAB, we have MATLAB answers. That means if users of MATLAB have some questions, there's a forum where you can ask these questions and people can answer there. So there's MATLAB answers, then there's MATLAB Central and MATLAB file exchange, where users who build MATLAB products, MATLAB toolboxes or some additional tools using MATLAB, they can post it on file exchange, which are free for download. You can use it and download it. Similarly, we have something known as MATLAB courseware. So if one of you can put that in the chat window, that would be awesome. MATLAB courseware is something that might be very useful to you. where a number of professors have curated courses that are based on MATLAB. Like we have courses on engineering design, we have courses on process control, we have courses on system dynamics and so on. So all these robotics and a number of courses, electrical engineering courses and all, which are already available. The entire course material, the code, the apps that are related, all of them are available. So you can download the entire course material and use it, and it's free again. Can be used without any royalties and so on.
Sure. Thank you, Spandhana and Amith. So there is one more question. What are all the mathematical skill one should need for Simulink? Spandhana, Amith, do you want to take it up?
I request, can you turn a video, those who are answering?
Yeah.
Sure.
Hello.
Yeah.
Right. So I'll take that. So for Simulink, Simulink is really a dynamic system sort of modeling platform. And so some of the topics that might be important to be familiar with is definitely differential equations, and we have a lot of like Spandhana mentioned coursework on that. Calculus generally, differential equations is a subset in some sense, but generally calculus and potentially some differential equations is a bare minimum, I'd say. But Spandhana, do you have other suggestions there?
Yeah, I want to add one point at this time,
Yeah.
Mr. So I have experience in solving differential equations using MATLAB. So during my PhD, I developed some mathematical models. I took 3 years to integrate one equations.
Right.
At last, to find the solution, I used MATLAB to find the results, and I got very good results. And that paper has been published in a very good leading journal. So it's very good to go with MATLAB.
Right. Thank you for the vote of confidence, Professor, for us. Yes. So those are, in my experience, the basic mathematical knowledge you may need to have, and there are also there's code and examples that we can share with you to learn more of this.
So there is one more question in hydraulics and pneumatic area. Can we do programming like what we're doing in PLC? So just before Amith or Spandhana answers this question, I would like to request all the participants to kindly go to the feedback form and provide us with your valuable feedback. I have pasted the link to the feedback in the chat window. Those who have done it, thank you very much for that. I would really request all of you to kindly fill out the feedback form. This will help us. Yeah, Amith, Spandhana, do you want to take up the hydraulic and pneumatic part?
Let me take that question. So regarding use in hydraulic or pneumatic controls, there are some examples that we can share on the chat window here. With respect to PLCs, I'm not quite familiar, but for control systems aspect, typically people do use Simulink, and we have a number of examples that we can share. It need not necessarily be in hydraulic or pneumatic actuation and control, but in a number of various domains as well with respect to control systems.
Right. And if I can add, for the PLC part, we have tools to generate code too. It's called PLC Coder. Unfortunately, it's not my area of expertise either, so I don't want to say wrong things there. But generally, and we can share a link to the PLC Coder tool too, and it potentially may have features and functions for. So Nikhil just shared it right now. Thank you, and Spandhana. So if you look through that and if you find more questions, you can please reach out to us and we can try to help you more.
There's one more question. Can we design an electric engine using Simulink for e-vehicles? Simulink is a major thing for model-based design. So yeah, would you like? I think we explained regarding the ether energy. Would you like to take up this question?
Yep. So right. So there are several blocks for different parts of your electric engine. All the electrical components, all the way down from discrete components like resistors and inductors, all the way to drives and the electromechanical components as well, right? So there are sort of basic blocks for all of them, or most of them. I won't say all of them, because there could be more that we are not aware of, right? There are blocks for that, and so you can sort of build on top of them. It's kind of like we give you the building blocks, and then you put them together and build these bigger machines, right? I don't know if there are examples that we can share already of such systems, but like ether energy, right? So they did they designed their system using Simulink, so it should be possible to do that.
Right. That's great. So I think so with respect to engaging with the curriculum, I see a question with respect to engaging with respect to curriculum and research. We would be very happy, to get in touch with you and take those projects up as well. So we would like to request you to kindly fill up the feedback form so that we'll be able to get back to you with respect to how we can engage with the college to do that.
If I can add very quickly, I saw a question here about Arduino. And so that's one very popular low-cost hardware platform for which we have a lot more support than otherwise, right? So there are blocks in Simulink which are meant for Arduino, meaning there are blocks that can point to certain pins that you can connect sensors and things like that. Using the Arduino platform. So as a student and as a faculty, sort of getting started in teaching hardware, software, sort of topics like these, embedded topics like these, for example, there's a lot of support for those frameworks.
Yeah. Thank you so much. And I think so. All the questions have been answered. I think so. So I think Mr. Vinay.
Yes, Professor. So I think
Yeah.
we have answered some of the major questions, and also Nikhil, Spandhana, and Amit have been really helpful in answering them in the chat window as well. If there are still any questions, please do feel free to reach out to us through our feedback forms. We'll be very happy, to take them up, and we will be happy to reach you back as well. So with that, Professor, I think since we are on slightly over time, I'm sorry for that, but then I hope it was very useful for all of us here.
Also, we'll be coming back tomorrow with a webinar on teaching with MATLAB. So for those of you who have questions on how to integrate MATLAB in curriculum and how to teach in this teach in online mode going forward for the next semester, we have a number of tools that could be useful to you. So you can try to attend tomorrow's session to know more about how you can use MATLAB for teaching your courses.
Yeah. So those who joined today, you can use the same link to join tomorrow also. So you do not need to wait for our mails. And please fill the feedback form, which is sticked on the chat window. So please don't forget. And thank you, Dr. Spandhana, Mr. Amit, and Mr. Vinay, and Mr. Nikhil for your time. Even though you might be busy with your schedules. And thank you so much. And this will be a great eye-opener for all the participants. And I hope tomorrow, when you attend tomorrow further, so that will be adding value to your today course also, I believe. So let me welcome you all tomorrow too by using the same link to enhance your fundamentals and MATLAB and get the things from the MATLAB. Okay.
Sure,
So
sir.
thank you so much. We will meet in tomorrow, Venus. Thank you so much.
Thank you very much. Bye.
Yeah. Bye.
Thank
Take
you.
care.
Bye.
Bye. Bye. Bye.